March 8, 1944, Rechlin-Lärz airfield, Mecklenburg, Germany. The morning air carried the sharp scent of aviation fuel and cold metal as Hauptmann Werner Baumbach walked across the tarmac toward a peculiar silver cylinder lying on a wooden examination table. Around him, a team of Luftwaffe engineers stood in silence, their breath visible in the early spring chill. The object before them was unremarkable in appearance, roughly 9 feet long and 2 feet in diameter, painted in a dull silver finish that caught the weak sunlight. One of the engineers had already scraped away a section of the paint near the tail cone, revealing something that shouldn't have been possible. The external fuel tank was made of paper. Baumbach ran his hand along the surface. The texture was wrong for metal. Even through his leather gloves, he could feel it, a subtle flexibility that aluminum would never possess, a slight give when pressure was applied. He removed his glove and touched the exposed section where the paint had been removed. Layers. Multiple thin sheets of heavy craft paper, each perhaps 0.5 millimeter thick, pressed together with some kind of resinous adhesive. The construction was sophisticated, purposeful, and engineered. This was not improvisation born of desperation. This was industrial optimization at a scale that made his calculations from the previous evening seem inadequate. The captured Mustang had arrived at Rechlin 2 days earlier, transported by rail from a crash site near Brandenburg. The pilot, a young American whose navigation chart still lay in the cockpit, had not survived. But the airframe remained largely intact, and, more importantly, intelligence officers had recovered 2 of these silver cylinders from fields northeast of Berlin, where they had been jettisoned during the air battle on March 6. 48 hours later, Baumbach and his team had completed their initial assessment. The mathematics were undeniable. The Americans had solved the escort fighter problem, and the solution was lying on this table, constructed from materials Germany couldn't spare even if the design could be replicated. The first reports had seemed impossible. On March 4th, American single-engine fighters appeared over Berlin, escorting bombers to the capital and returning to England. Luftwaffe intelligence had calculated repeatedly that no single-engine fighter possessed sufficient range for such a mission. The distance from English bases to Berlin measured approximately 560 miles one way. Standard fighter aircraft, even with external fuel tanks, could not carry enough fuel for a round trip exceeding 1,100 miles while maintaining combat capability. This assessment had been based on thorough analysis of captured P-47 Thunderbolts and P-38 Lightnings, both of which had demonstrated clear fuel limitations that forced them to turn back hundreds of miles before reaching the German capital. Yet on March 6th, approximately 660 bombers had attacked Berlin in daylight, escorted by over 150 P-51 Mustangs, along with P-38 Lightning and P-47 Thunderbolt groups. The escort fighters had engaged Luftwaffe interceptors over Berlin itself and accompanied the bombers home. This was not a fluke. The Americans had fundamentally changed the strategic equation. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. General Major Adolf Galland had flown combat missions during this period despite his administrative position as General der Jagdflieger. An ace with over 100 confirmed victories, Galland understood fighter combat as well as any pilot in the Luftwaffe. He had encountered P-51 formations over Germany and immediately recognized what others were slow to accept. In his combat assessment submitted through official channels, he noted that American fighters were operating at full combat capability over Berlin, engaging aggressively with no apparent fuel conservation behavior. They were not flying at the extreme limits of their range. They had reserves. This contradicted everything Luftwaffe intelligence believed about American fighter capabilities. Galland's reports had emphasized the P-51's superior performance at high altitude, where it outmatched both the Messerschmitt Bf-109 and Focke-Wulf FW-190 in speed and maneuverability above 20,000 feet. But what troubled him more than the aircraft's performance was its presence. How had the Americans achieved this range? What has changed in the 2 months since the last assessment of captured American fighters? The technical examination at Rechlin focused on answering precisely this question. Baumbach's team had measured the P-51B's internal fuel capacity with Germanic precision. The aircraft featured 2 wing tanks, each holding 92 gallons of aviation fuel, for a total of 184 gallons in the wings. Additionally, the fuselage contained an 85-gallon fuel tank positioned directly behind the cockpit. This fuselage tank was a relatively recent addition to the P-51B design, incorporated during production to extend range. Total internal fuel capacity was 269 gallons. The Packard-built Merlin engine, a license-produced version of the Rolls-Royce Merlin that had transformed the Mustang's high-altitude performance, consumed fuel at rates that varied with power settings. At economy cruise settings, the engine burned approximately 60 gallons per hour. At normal cruise power, consumption increased to approximately 75 gallons per hour. German engineers performed range calculations using these figures with the methodical thoroughness that had made German technical intelligence among the most accurate in the war. With 269 gallons of internal fuel and consumption of approximately 70 gallons per hour at cruise settings, the P-51B could fly for roughly 3.8 hours. At the aircraft's cruising speed of approximately 300 miles per hour, this yielded a maximum range of 1,140 miles. This was precisely enough to reach Berlin from English bases and return, but only barely, with virtually no reserves for combat operations. Yet combat reports clearly indicated the American fighters had engaged in prolonged dogfights over Berlin, sometimes lasting 15 to 20 minutes before disengaging and flying home. Combat power settings consumed fuel at rates exceeding 100 gallons per hour. Such fuel expenditure should have left the aircraft unable to complete the return journey. Multiple pilots had reported being pursued by Mustangs well past the point where fuel considerations should have forced the Americans to break off engagement. The calculations did not explain what German pilots were observing in the skies over their homeland. The answer lay in the silver cylinder on the examination table. The P-51B featured standardized hardpoints under each wing designed to accommodate external stores. These attachment points included fuel line connections, indicating they were designed specifically for external fuel tanks. Drop tanks were not a new concept. The Luftwaffe had used them extensively since the Battle of Britain. The Bf 109 could carry a 300-litre drop tank. The FW-190 regularly employed them for extended-range missions. Drop tanks allowed aircraft to carry additional fuel externally, then jettison the empty tanks before entering combat to reduce weight and drag. This was standard practice for all air forces. The question was not whether the Americans were using drop tanks, but rather what capacity these tanks had, and, more troublingly, how the Americans were producing enough of them to maintain operational tempo. A metal drop tank required aluminum, specialized metalworking equipment, skilled labor, and significant production time. If the Americans were manufacturing metal tanks in sufficient quantities to equip hundreds of fighters for daily missions deep into Germany, their industrial capacity exceeded even the most pessimistic German estimates. The search for American drop tanks from the March missions had begun immediately after the first Berlin raid. Intelligence officers plotted likely jettison points based on engagement locations reported by Luftwaffe pilots. Drop tanks would typically be released when enemy fighters were encountered, as the external stores reduced maneuverability and speed. Search teams composed of Wehrmacht personnel and Hitler Youth volunteers spread across the countryside northeast of Berlin, looking for any debris from the air battles. Within 3 days, several objects were recovered from fields and forests in the region. Most were fragmentary, crushed on impact or damaged by the fall, but 2 examples arrived at Rechlin in relatively intact condition, having landed in soft soil or winter wheat that cushioned their impact. What the engineers found revolutionized German understanding of American industrial methods and confirmed fears about the true scale of Allied material superiority. The captured drop tanks were cylindrical, measuring approximately 108 inches in length, with a diameter of roughly 22 inches at the widest point. Capacity calculations indicated each tank held approximately 108 United States gallons, or 400 liters. Two such tanks would provide 216 additional gallons of fuel, extending the P-51's total fuel capacity to 485 gallons. With this fuel load, the Mustang could fly for approximately 6.7 hours at cruise power settings, yielding a range exceeding 2,000 miles. This was more than sufficient for the Berlin mission with substantial combat reserves. The fuel capacity mathematics now made complete sense. A Mustang could cruise to Berlin, fight for 20 minutes at high power settings, and still return to England with fuel remaining. But what immediately captured the attention of Baumbach and his engineering team was not the capacity of the tanks, but rather their construction. The implications were staggering. The drop tanks were not made of metal. When engineers carefully scraped away the silver paint coating near the tail cone, they found multiple layers of heavy paper, each layer compressed and laminated together with a resinous adhesive. The construction was sophisticated and purposeful, far removed from the crude improvisation one might expect from a nation struggling with material shortages. The nose cone and tail cone were formed from overlapping pieces of the paper material, pressed into shape through a process similar to papier-mâché. Each piece was visible as a slight ridge where it overlapped with adjacent pieces, creating a scalloped texture. The center section was seamless, wrapped around a cylindrical form in continuous layers. The fuel fittings were brass, precisely machined and properly sealed against leakage. Peering through the filler cap revealed an interior coated with what appeared to be a cellulose-based lacquer designed to resist the corrosive effects of aviation gasoline. German materials specialists were brought in to analyze the tank's construction in forensic detail. The paper was identified as kraft paper, manufactured using a chemical pulping process that produced exceptionally strong cellulose fibers. This was the same material used for heavy-duty shipping containers and industrial packaging, materials Germany itself used extensively, but could not spare for non-critical applications. The adhesive proved to be a resorcinol formaldehyde resin, a thermosetting polymer that created bonds stronger than the paper itself when heat-cured. The lamination involved at least 12 separate layers of paper, each one carefully oriented to provide strength in multiple directions, creating a composite structure that could withstand the pressure differential at altitude and the stresses of high-speed flight. Internal baffles made of thin wood were installed to prevent fuel from surging during maneuvers, a detail that spoke to careful engineering rather than expedient substitution. The entire construction process was clearly standardized and designed for mass production in facilities that required no specialized metalworking equipment. Most significantly, the empty tank weighed approximately 80 pounds, compared to 65 to 75 pounds for a comparable metal tank of smaller capacity. The paper construction was not significantly lighter than metal, eliminating weight savings as the primary motivation. The advantages lay elsewhere, in realms that made the engineering team profoundly uneasy. The implications spread through the room like a physical force. Baumbach looked at the faces of his colleagues and saw his own realization reflected back. The Americans were manufacturing fuel tanks from non-strategic materials. Paper and wood-based resins did not require aluminum, steel, or other metals that were increasingly scarce in wartime economies. The manufacturing process required no specialized metalwork equipment, no skilled metalworkers, no welding or forming of sheet metal. These tanks could be produced in any paper mill or packaging factory, with relatively simple modifications to existing equipment. The United States had hundreds of such facilities. If even a small percentage of American paper production had been converted to drop tank manufacturing, output could reach thousands of units per week. The tanks appeared to have no serial numbers, no manufacturer markings, nothing to indicate limited production runs or careful inventory control. They were commodity items, mass-produced and completely expendable. One of the engineers voiced what everyone was thinking. They're throwing them away. They fill them, fly them for a few hours, and discard them over Germany. They don't even try to recover them. Intelligence officers began researching American paper industry capacity. The data they uncovered was sobering. The United States produced approximately 12 million tons of paper annually before the war, with production increasing during wartime mobilization. Converting even 1% of this capacity to drop tank production would yield over 100,000 tanks per month, far exceeding any plausible requirement for P-51 operations. The real constraint would not be materials, but rather the availability of manufacturing equipment and labor to assemble the tanks. But this was precisely the type of manufacturing that could be performed by semi-skilled workers after minimal training. The paper tanks represented industrial efficiency and resource optimization on a scale that German planners found difficult to comprehend. Germany's economy was organized around skilled craftsmen, producing precision equipment in limited quantities. The German approach created superior individual items, but at the cost of production speed and volume. The Americans had chosen a different path, designing for mass production from the outset, accepting adequate performance in exchange for overwhelming quantity. Further analysis revealed additional details about the paper tank's design and operational use. The tanks were strictly single-use items. The resinous adhesive, while creating strong bonds when cured, was slowly dissolved by prolonged contact with aviation gasoline. Intelligence reports and interrogations of captured American aircrew indicated that paper tanks had to be filled immediately before flight and could not be stored for more than a few hours without developing leaks. This was not a limitation that affected operational use. Fighters were fueled as part of their pre-flight preparation. The tanks would be used for a few hours during the mission, then jettisoned over enemy territory or the North Sea. The single-use nature actually simplified logistics. There was no need to recover and reuse the tanks, no need for cleaning, inspection, or maintenance infrastructure. They were expendable by design, a philosophy that struck at the heart of German engineering principles. The evaluation also noted the color coding of the tanks. Paper drop tanks were painted silver, while metal tanks used by American forces were painted gray or olive drab. This color distinction allowed ground crews to quickly identify tank types during fueling operations, preventing confusion that could delay mission launches. The silver finish on paper tanks also helped reflect solar heat, reducing fuel evaporation and vapor pressure issues at altitude. Every aspect of the design reflected systematic engineering optimization for mass production and field use. By late March 1944, German intelligence had traced the origin of the paper drop tanks to British development. The Air Ministry in London had commissioned development of impregnated paper fuel tanks in 1943 to conserve strategic metals, particularly aluminum. The Bauoto Scott Corporation, utilizing expertise in paper manufacturing, developed the production process. The tanks entered service with RAF fighter squadrons in late 1943. American forces quickly adopted the design, with multiple manufacturers in both Britain and the United States producing tanks for use by USAAF fighter groups. The innovation had been driven by British resource scarcity, a response to the U-boat blockade and the demands of total war mobilization, but it was being exploited on a massive scale by American industrial capacity. The British had created the solution. The Americans had turned it into an industrial flood. This partnership, this combination of British ingenuity and American manufacturing scale, represented a strategic advantage that Germany could not counter through tactical excellence or technical sophistication. Baumbach prepared his report for submission to the Reich Air Ministry. The technical findings were straightforward and damning. The P-51 Mustang, equipped with two 108-gallon drop tanks manufactured from paper and resin, possessed a combat radius exceeding 800 miles. This was sufficient to escort heavy bombers to any target in Germany and return to England with fuel reserves for extended combat operations. The drop tanks were manufactured from non-strategic materials, using mass production techniques that allowed output in the thousands per week. The Americans had effectively removed range as a limiting factor for fighter escort operations. The strategic implications section of his report was harder to write. Baumbach was a technical officer, not a strategic analyst, but the thick conclusions were inescapable. The Americans could now bomb any target in Germany with fighter escort throughout the entire mission profile. The Luftwaffe's defensive strategy, which had relied on forcing Allied fighters to turn back due to fuel limitations, was obsolete. German fighters would have to engage American escorts to reach the bombers, and those engagements would cost aircraft and pilots at rates Germany could not sustain. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The broader implications extended far beyond fuel tanks. German technical staff began a systematic review of captured American equipment, looking for other examples of industrial innovation and mass production techniques that might reveal the true extent of Allied material superiority. The results painted a consistent and troubling picture. American equipment was not always technologically superior to German equivalents in terms of individual component performance. German optics were often better. German small arms were often more sophisticated in design. German armor metallurgy was in some respects more advanced, but American equipment was consistently better manufactured, more standardized, more reliable, and available in vastly greater quantities. The American approach prioritized producibility over perfection. Components were designed from the outset for mass production by semi-skilled workers using standardized tooling. Parts were interchangeable between units without hand-fitting or modification. Assembly line methods reduced production time and increased output to levels that seemed almost incomprehensible to German engineers accustomed to craft production methods. The contrast with German production methods was stark and sobering. German weapons and equipment were often technical masterpieces, hand-fitted by skilled craftsmen to tolerances measured in microns. A German tank or aircraft engine represented the peak of precision engineering, a marriage of metallurgy, design, and craftsmanship that produced machines of extraordinary capability. But building such equipment required skilled labor that took years to train, specialized tools that took months to manufacture, and significant time per unit that limited production rates. Germany built superior individual items. The Americans built adequate items in overwhelming quantities. In industrial warfare, quantity was proving decisive. A technically perfect fighter that took 3 months to build was less valuable than 3 adequate fighters that could be built in the same time span. A precisely machined engine component that required a master machinist was less useful than a stamped component that could be produced by a semi-skilled worker in a fraction of the time. Analysis of P-51 Mustang production illustrated this principle with brutal clarity. North American Aviation had designed the original Mustang prototype in response to a British requirement in 1940. The prototype, designated NA-73X, was completed just 117 days after the contract was signed, one of the fastest design to prototype cycles in aviation history. The first flight occurred on October 26, 1940. By 1944, North American was producing P-51 variants at 2 facilities, running at peak efficiency. The Inglewood plant in California averaged approximately 364 Mustangs per month during peak production periods. The Dallas plant contributed additional production at similar rates. Combined output across both facilities reached an average of approximately 574 P-51s per month during 1944, with production accelerating throughout the year. Peak monthly production would reach 881 aircraft in January 1945. Each P-51 required approximately 15,000 individual parts, manufactured by hundreds of subcontractors across the United States. The Packard-built Merlin engines were produced in Detroit at rates exceeding 300 units per month. Final assembly of a P-51D required approximately 22,000 man-hours of labor, but the production line system meant that completed aircraft rolled out of the factory at intervals of a few hours. At peak efficiency, a new Mustang was completed approximately every 2 hours, day and night, 7 days a week. The scale and efficiency of this production system exceeded anything Germany had achieved or could hope to achieve under current circumstances. Messerschmitt and Fokker-Wulf combined produced approximately 600 fighters per month in early 1944, Despite operating under emergency priority programs and utilizing forced labor from concentration camps and occupied territories, German aircraft production could not match American output. The disparity was widening, not narrowing. The resource implications were equally sobering and provided context for why the Americans could afford to manufacture drop tanks from paper as an optimization choice rather than desperate necessity. American aluminum production in 1944 reached approximately 1.25 million tons, equivalent to £2.5 billion annually. This represented a massive increase from pre-war production of approximately 164,000 tons in 1939. Germany's aluminum production, by contrast, peaked at approximately 250,000 tons per year and was declining due to bombing of production facilities and loss of bauxite sources in occupied territories. The Americans had approximately 10 times Germany's aluminum production capacity. The decision to manufacture drop tanks from paper rather than aluminum was not driven by metal scarcity. The United States had sufficient aluminum to produce every drop tank in metal if desired. Paper was chosen because it was cheaper, required less critical manufacturing equipment, freed aluminum for other uses such as aircraft, airframes, and engines, and could be produced more quickly with less skilled labor. This was optimization for efficiency, not desperation born of shortage. The psychological impact of this realization spread through the Luftwaffe technical and operational communities like a virus. The paper drop tank became a symbol of American industrial capability and the fundamental disparity in resources between the combatants. Captured examples were displayed at technical briefings for Luftwaffe personnel throughout the spring and summer of 1944. Pilots transitioning to fighter units were shown the tanks and asked to calculate the implications for combat tactics. The message was unmistakable and deliberately sobering. American fighters could now escort bombers anywhere in Germany. The previous defensive strategy of waiting for Allied fighters to reach their fuel limits and turn back was obsolete. Luftwaffe fighters would have to engage the escorts to reach the bombers, and those engagements would cost aircraft and pilots at rates Germany could not sustain. Galland provided the operational assessment in conferences with senior Luftwaffe leadership throughout the spring of 1944. The P-51 was superior to German fighters above 20,000 feet. He emphasized repeatedly in reports that grew increasingly urgent in tone. It was faster than the Bf-109 at altitude and more maneuverable than the Fw-190. With the extended range provided by drop tanks, it could escort bombers throughout their mission profile. German fighters could no longer attack bomber formations unopposed after Allied escorts turned back. Every intercept now required fighting through the fighter screen. Loss rates were climbing steadily, and the trend was unsustainable. In January 1944, the Luftwaffe lost approximately 90-day fighters defending the Reich, while claiming approximately 150 Allied aircraft destroyed. The exchange ratio, while unfavorable, was at least comprehensible within traditional combat mathematics. By February, German losses had increased to approximately 160 aircraft against approximately 230 Allied losses. The numbers were worsening, but still within the realm of what German replacement capacity could theoretically sustain if pilot training could keep pace. March brought the Berlin missions and a fundamental shift in the strategic equation. The appearance of P-51s over the capital forced the Luftwaffe to commit fighters to defend targets they had previously considered beyond effective Allied reach. German losses in March exceeded 200 fighters, with particularly heavy casualties during the large-scale battles over Berlin on March 6th and 8th. More troubling than the absolute numbers was the quality of pilots being lost. Experienced fighter leaders, men with hundreds of combat hours and dozens of victories, were being killed at rates that left squadrons without effective leadership. The summer of 1944 brought the full impact of American escort fighter capability crashing down upon the Luftwaffe with catastrophic force. The 8th Air Force conducted deep penetration raids almost daily when weather permitted, striking targets across Germany with a systematic thoroughness that left no major industrial center untouched. Mustangs provided continuous escort from England to targets deep inside the Reich and back, their silver wings catching the sun at 30,000 feet as they wove protective patterns above the bomber formations. Luftwaffe fighter losses mounted at rates that shocked even pessimistic analysts. In June 1944, approximately 350-day fighters were lost, defending the Reich, representing losses that exceeded monthly production. German factories were building fighters faster than ever before, but the Luftwaffe was losing them faster than they could be delivered to operational units. In July, losses exceeded 350 single-engine fighters in the West alone, representing a 31.2% monthly attrition rate. This meant that nearly one-third of all operational fighters in the West were lost in a single month. August saw similar losses with a 36% attrition rate, a figure so catastrophic that it meant the average fighter pilot had a statistical life expectancy of less than 3 months in combat. At these loss rates, experienced pilots were being killed faster than training schools could produce replacements, and the replacements arriving from training were woefully unprepared for the combat conditions they faced over Germany. The replacement pilots arriving from training schools had perhaps 150 hours of total flight time, compared to 300 hours or more for American pilots entering combat. Fuel shortages forced Germany to reduce training hours continuously throughout 1944. By summer, some replacement pilots had as little as 30 hours in type before being assigned to operational squadrons. These young men, barely out of their teens, were thrown into combat against American pilots who had hundreds of hours of combat experience, flying aircraft with superior high-altitude performance, supported by overwhelming numerical superiority. The experience gap, combined with numerical inferiority and the constant presence of P-51 escorts, made daylight operations over Germany increasingly deadly for Luftwaffe pilots. A replacement pilot's first mission was often his last. Squadron commanders reported that newly arrived pilots frequently failed to return from their initial combat sortie, killed before they could learn the survival skills that might have kept them alive. The Luftwaffe was consuming its future, burning through young pilots at rates that made eventual defeat not just likely but mathematically certain. Galland submitted repeated assessments to Hitler and senior Wehrmacht leadership throughout this period, each report more urgent than the last. His September 1944 report stated the situation with brutal honesty that would contribute to his eventual removal from command. The Luftwaffe could not win the air war. Germany lacked the resources, the fuel, the aircraft, and most critically, the trained pilots necessary to contest Allied air superiority. The Americans could replace losses faster than Germany could inflict them. Their industrial capacity was beyond Germany's ability to counter through combat operations alone. The only viable strategy, Galland argued, was to husband remaining resources for defense of critical targets and hope for a political settlement before complete collapse. This assessment was not well received. Hitler demanded offensive action and refused to accept that the Luftwaffe had lost the initiative permanently. But Galland's analysis was based on mathematics that admitted no political interpretation. The numbers were clear, and they pointed toward inevitable defeat. The paper drop tanks continued to fall across Germany throughout late 1944 and into 1945, silent witnesses to the industrial disparity that was deciding the war. German civilians learned to recognize the distinctive cylindrical shapes lying in fields and forests, their silver paint gleaming in the sun. Initial reports sometimes described them as unexploded bombs, causing local panic until military authorities identified them as harmless fuel tanks. Instructions were distributed through civil defense organizations, explaining that the silver cylinders falling from Allied aircraft were empty fuel tanks, not weapons, and posed no danger unless handled carelessly. Citizens were instructed to report their locations to local authorities but not to approach them, as aviation gasoline residue could be flammable. The psychological impact was noted in civilian morale reports compiled by security services. The sight of enemy aircraft overhead in such numbers that their contrails crisscrossed the sky, casually discarding expendable fuel tanks like litter, reinforced the message that the Allies had resources to waste while Germany scraped for every litre of fuel and every kilogram of aluminum. Technical intelligence continued analysing captured American equipment throughout 1944, but the focus shifted from understanding capabilities to documenting the scale of industrial disparity for the historical record. The question was no longer whether Germany could match American production, but rather how wide the gap had become and whether it was still widening. The answer to both questions was deeply discouraging. Could Germany manufacture similar paper drop tanks? The technical answer was yes. The German chemical industry could produce suitable resins. German paper mills could manufacture kraft paper of adequate strength. The manufacturing process was not particularly sophisticated by German engineering standards. Any competent industrial facility could replicate the design with minor modifications to existing equipment, but the practical answer was an emphatic no, and the reasons revealed much about the difference between technical capability and industrial reality. Germany's chemical industry was already operating at maximum capacity, producing synthetic rubber to replace natural rubber supplies cut off by the Allied blockade, explosives for ammunition and bombs, propellants for rockets and artillery, and dozens of other critical materials. Resin production for non-essential items like drop tanks could not be prioritized when the same chemical feedstocks were desperately needed for more critical applications. The paper industry was fully committed to military requirements for maps, documents, packaging for supplies, and other essential uses. Most critically, there was no operational requirement for extended-range drop tanks when fuel shortages were grounding large portions of the Luftwaffe. By late 1944, fuel shortages had become the primary constraint on Luftwaffe operations. Pilot training was reduced to minimal levels, with some pilots receiving as little as 20 hours of flight training total before being assigned to operational units. Operational sorties were limited by fuel availability rather than aircraft availability. Squadron commanders reported having 30 aircraft, but fuel for only 10 sorties per day. Building drop tanks to extend range was meaningless when there was barely enough fuel for local defensive operations. The irony was stark and bitter to German planners who understood the implications. The Americans had solved the fighter range problem with paper fuel tanks manufactured from non-strategic materials at exactly the time when German fighters were grounded by fuel shortages. Different problems reflecting different industrial realities, leading to different outcomes that were deciding the war's trajectory. The Americans had more of everything. More aircraft rolled off production lines at rates that exceeded German monthly production in a single week. More fuel refined from Texas oil fields and Venezuelan crude. More pilots trained at facilities across the American South, where fuel was plentiful and training could be thorough. More aluminum smelted in plants powered by hydroelectric dams. More industrial capacity that could be redirected toward military production without causing civilian hardship. And sufficient excess capacity to optimize solutions like paper drop tanks, choosing the most efficient manufacturing method rather than being forced into substitutions by scarcity. Germany was fighting a war of scarcity against an enemy for whom scarcity was not a constraint but merely a variable to be optimized. This fundamental asymmetry made eventual defeat inevitable once American industrial mobilization reached full capacity. The outcome was determined not on battlefields but in factories, not by tactical skill but by production rates, not by courage but by resources. By January 1945, the war's outcome was beyond doubt, except to those who refused to see. Soviet forces were approaching the Oder River, less than 50 miles from Berlin, driving west through Poland with armies that outnumbered German defenders by factors that made defensive success impossible. Western Allied forces had recovered from the Ardennes offensive, Germany's last desperate gamble in the West, and were pushing toward the Rhine with overwhelming material superiority. The Luftwaffe could mount only sporadic resistance, limited by fuel availability and catastrophic pilot losses that had reduced many squadrons to paper organizations with aircraft but no qualified pilots to fly them. The systematic study of American equipment continued at Rechlin, but it had become an academic exercise, documentation for historians, rather than intelligence that could influence operations. The findings were recorded with the same professional thoroughness that had characterized German technical intelligence throughout the war, but they could no longer change outcomes that had become inevitable. The final comprehensive analysis of the P-51 and its drop tanks was prepared in late January 1945 by a team that included many of the engineers who had examined the first captured examples 11 months earlier. The report documented every technical aspect of the Mustang's range capability with exhaustive detail. The drop tank construction methods and materials were analyzed thoroughly, including photographs, material samples, and engineering drawings. Production estimates calculated American manufacturing capacity based on known paper industry output. Operational implications were assessed with brutal honesty. The conclusion was unambiguous and damning. The P-51 Mustang, equipped with expendable paper drop tanks manufactured from non-strategic materials, has rendered the German heartland indefensible against American daylight bombing. Germany lacks the industrial capacity to match American fighter production, the fuel to sustain combat operations at the required scale, the trained pilots to replace losses at current attrition rates, and most fundamentally, the resources to contest Allied air superiority over the Reich. The report was filed in the Reich Air Ministry archives in late January 1945. Whether senior leadership read it is unknown. By then, technical reports analyzing American capabilities were simply confirming what battlefield reality had already demonstrated with merciless clarity. The Luftwaffe, which had dominated European skies in 1940 and 1941, was reduced to occasional desperate sorties by early 1945, hoarding precious fuel for missions that could not change the strategic situation. American fighters roamed freely over Germany, attacking targets of opportunity, strafing trains and vehicles, establishing complete air supremacy that made ground operations nearly impossible during daylight hours. Each paper drop tank falling from American aircraft was a reminder of the industrial disparity that had decided the air war long before the final battles were fought. The June 1944 exhibition at Rechlin had displayed captured Allied aircraft to Luftwaffe personnel as part of a broader effort to educate German pilots about enemy capabilities. The exhibition included multiple examples of the P-51 Mustang, alongside B-17 and B-24 bombers, P-38 Lightnings, Lancaster bombers, Mosquito fighter bombers, Typhoon fighter bombers, and various Spitfire variants. Thousands of Luftwaffe pilots and ground personnel toured the exhibition, examining enemy equipment firsthand, touching the aluminum skin of American bombers, sitting in captured cockpits. The paper drop tanks were displayed prominently with technical diagrams explaining their construction and range implications in detail that left no room for misunderstanding. The exhibition served as both an educational tool and sobering reality check for pilots who would face this equipment in combat. German personnel could see the quality of Allied equipment, the standardization of components that indicated mass production, the evidence of industrial capacity that dwarfed Germany's remaining manufacturing base. The overwhelming scale of Allied industrial mobilization was made tangible through the physical examples of equipment they faced in combat daily. Walking through the exhibition, pilots could see not just individual aircraft but the industrial system that produced them. The interchangeable parts, the standardized instruments, the evidence of assembly line manufacturing that allowed production in quantities Germany could no longer match. Kampfgeschwader 200. The Luftwaffe unit responsible for special operations, including flying captured Allied aircraft for evaluation and clandestine missions, operated several P-51s throughout 1944. These aircraft, repainted in German markings but retaining their distinctive American lines, were used for evaluation flights that allowed Luftwaffe test pilots to experience firsthand the performance characteristics that made the Mustang such an effective fighter. The reports from KG-200 pilots consistently noted the P-51's excellent visibility from the cockpit, particularly in the later P-51D model, with its bubble canopy that provided unobstructed views in nearly all directions. The aircraft was stable in flight, responsive to controls without being twitchy, and possessed excellent high-altitude performance that German single-engine fighters could not match. The Merlin engine provided smooth, reliable power throughout the operating envelope, with none of the temperamental behavior that plagued some German designs. Most significantly, the range and endurance were extraordinary for a single-engine fighter. With full internal fuel and drop tanks, the P-51 could remain airborne for over 6 hours, flying missions that would have been impossible for German single-engine fighters, even with external tanks. This endurance translated directly into combat effectiveness, allowing American pilots to patrol at altitude for extended periods, waiting for German fighters to appear, engaging when tactically advantageous, rather than being forced to break off due to fuel constraints. The technical understanding gained at Rechlin contributed to German defensive tactics in the final year of the war, though the knowledge could not overcome material disadvantages. Recognizing that American fighters could escort bombers throughout their missions, Luftwaffe fighter controllers attempted to concentrate forces at specific points to achieve local superiority sufficient to break through the escort screen. This required careful coordination and timing, as dispersed German units had to assemble at designated locations to create formations large enough to have a chance against the heavily escorted bomber streams. Fuel constraints and communication difficulties often prevented successful concentration. Even when German fighters achieved favorable positions, the presence of P-51 escorts made attacks on the bomber formations extremely costly. The tactical situation had fundamentally shifted from the dynamics of 1943. In that earlier period, unescorted or poorly escorted bomber formations had suffered catastrophic losses at the hands of German fighters operating with tactical and numerical advantages. By mid-1944, German fighters attempting to reach the bombers suffered catastrophic losses, forced to fight through escort screens that cost them aircraft and pilots before they could even engage the bombers. The paper drop tanks themselves became collector's items after the war, though very few examples survived intact. Most were destroyed on impact when jettisoned at high altitude, or deliberately crushed by Allied ground crews to prevent reuse by enemy forces in the unlikely event they fell into German hands. The expendable nature of the tanks meant they held little intrinsic value and were not preserved deliberately. The few that survived became museum artifacts and historical curiosities, physical evidence of industrial innovation during total war. The National Air and Space Museum in Washington maintains several examples in its collection, displayed alongside the P-51 Mustang aircraft they were designed to serve. The information placards note the construction from laminated craft paper, impregnated with phenolic resin, the manufacturing by companies like Bowater Scott in Britain and various contractors in the United States, and the capacity of 108 United States gallons. The placards do not typically mention that German engineers spent weeks analyzing these tanks, calculating their implications, and understanding through them the full scale of Allied industrial superiority that would determine the war's outcome. The story preserved in technical reports and post-war interviews reveals the psychological impact on German technical personnel who examined the captured tanks. They were not analyzing a superior weapon in the traditional sense. The paper drop tank was not an advanced technology representing scientific breakthrough or engineering innovation. It was, in fact, a deliberately simplified design using non-critical materials, chosen specifically because they were abundant and easily worked. But that very simplicity carried a message more devastating than any technical sophistication could have conveyed. The Allies had such overwhelming industrial capacity that they could afford to optimize designs for mass production rather than performance. They could manufacture fuel tanks from paper because they had unlimited paper, unlimited resin, unlimited manufacturing capacity, and unlimited fuel to put in the tanks. The optimization was not driven by scarcity, but by efficiency. The choice to use paper was made from a position of strength, not weakness. Germany's experienced engineers understood immediately what this meant, and the understanding was profoundly demoralizing. They were not fighting an enemy that was desperately improvising with substitute materials due to shortages. They were fighting an enemy so wealthy in resources that substitution was a choice made for efficiency, not a necessity imposed by shortage. The difference was fundamental, and revealed the true nature of the strategic imbalance. Post-war interrogations of Luftwaffe personnel consistently returned to this theme when officers were asked about turning points in the air war. When asked when they first understood that Germany would lose the war, many technical staff and senior officers cited the early spring of 1944 as the moment when hope gave way to grim realization. The arrival of long-range fighter escorts over Berlin marked a decisive shift in the strategic balance that could not be reversed through tactical adjustments or operational innovation. Hermann Göring, interrogated after the war by American intelligence officers, acknowledged that long-range fighters had delivered a major strategic blow to German defensive planning and were among the most decisive factors in the ultimate outcome of the air war. While specific quotes attributed to Göring about seeing Mustangs over Berlin remain difficult to verify in primary sources, his post-war statements documented in Allied interrogation records consistently acknowledged that Allied air superiority, made possible by long-range escort fighters, had been decisive in Germany's defeat. The technical lessons learned by German engineers who examined captured P-51s and their drop tanks contributed to post-war aviation development in ways that extended beyond immediate military applications. Many of these engineers immigrated to the United States or worked with Allied technical intelligence services after the war, bringing their detailed understanding of both German and Allied design philosophies to post-war aerospace development. Their emphasis on standardization, interchangeability of parts, and design for manufacturability became standard practice in post-war aircraft development across the Western Alliance. The paper drop tank itself became a case study in wartime industrial innovation, taught in engineering schools and military staff colleges as an example of how resource optimization and mass production could provide strategic advantage. The lesson was clear. Effective solutions need not be sophisticated or technically impressive. A tank made from glued paper, designed for single use, manufactured from non-critical materials, represented an appropriate solution to the specific problem of extending fighter range. It was good enough for the mission, and good enough proved to be exactly right. The P-51 Mustang continued in service with various air forces for decades after World War II, testament to the soundness of the basic design. The aircraft saw extensive combat in the Korean War from 1950 to 1953, serving primarily in ground attack and close air support roles. The excellent range and endurance that had made it an outstanding escort fighter in Europe proved equally valuable in the very different operating environment of Korea, where close air support for ground forces became the primary mission. P-51s remained in frontline service with some air forces into the early 1980s, an extraordinary service life for a design that first flew in 1940. More than 15,000 Mustangs were produced during and immediately after the war, making it one of the most numerous American fighters of the era. Today, over 100 P-51s remain airworthy, maintained by collectors and museums worldwide. The sight of a Mustang in flight, often still wearing the distinctive markings of wartime units, serves as a reminder of the aircraft's role in establishing Allied air supremacy over Europe. The broader historical significance of the P-51 and its paper drop tanks extends beyond their tactical and operational impact to encompass fundamental lessons about industrial warfare and the importance of production. Capacity in modern conflict. World War II was decided not primarily on battlefields, but in factories. The side that could produce more weapons, more ammunition, more aircraft, more vehicles, and more supplies faster than they were consumed in combat, held a decisive advantage that tactical skill and operational excellence could slow but not overcome. The United States achieved industrial mobilization on a scale unprecedented in history. Peak wartime production in 1943 to 1944 saw American factories producing aircraft at rates exceeding 50,000 per year, ships at rates of multiple vessels per day, tanks and vehicles in quantities measured in tens of thousands, and ammunition in quantities measured in billions of rounds. This industrial output supported not only American forces deployed across the Pacific and European theaters, but also supplied substantial quantities of equipment to Britain, the Soviet Union, and other Allied nations through Lend-Lease programs. Germany, despite possessing significant industrial capacity and technical expertise, that in many areas matched or exceeded Allied capabilities, could not match Allied production rates. The reasons were multiple and cumulative: a smaller industrial base compared to the PERND, combined Allied economies, strategic bombing of production facilities that disrupted output, loss of access to raw materials as territory was lost to advancing Allied forces, diversion of resources to competing priorities, including wonder weapons of questionable strategic value, and inefficiencies in organization and planning that hampered optimal resource allocation. But perhaps most fundamentally, Germany was fighting a coalition whose combined industrial capacity was several times larger than its own. The addition of American industrial might to the Allied cause in 1942 to 1943 made Axis defeat inevitable once that industrial capacity reached full mobilization. The question was not whether Germany would lose, but how long the war would continue and at what cost in lives and destruction. The paper drop tanks falling across Germany in 1944 to 1945 symbolized this industrial reality in a form so simple and so stark that its message could not be misunderstood. The examination of captured American equipment by German technical intelligence services had been systematic and professional throughout the war. Facilities like Rechlin maintained detailed records of performance testing, material analysis, and technical assessments with the thoroughness characteristic of German technical work. These documents, many of which survived the war in various archives, including the Bundesarchiv, provide valuable historical insight into how each side viewed the other's capabilities. German assessments of American equipment were generally accurate in technical terms. They correctly identified strengths and weaknesses of American aircraft, vehicles, and weapons systems. Their performance predictions proved reliable when compared to actual combat results. Where German analysis failed was not in understanding individual items, but in comprehending the scale of American production and the implications of that scale for the war's outcome. A single P-51 Mustang was a very good fighter aircraft, superior to most German fighters at high altitude. 10,000 P-51 Mustangs represented air superiority that no tactical skill or technical innovation could overcome. The story of German engineers examining paper drop tanks at Rechlin in March 1944 is ultimately a story about the nature of industrial warfare in the 20th century. It demonstrates that in conflicts between industrialized nations, production capacity becomes as important as battlefield prowess. The side that can build more, build faster, and build more efficiently holds advantages that tactical and operational excellence cannot fully compensate for overextended periods. This lesson, learned at great cost by Germany and Japan in World War II, influenced military planning throughout the Cold War and continues to inform strategic thinking today. The ability to sustain production of advanced weapons systems, to maintain supply chains under stress, to train personnel faster than they are lost in combat, and to outproduce an opponent over extended periods remains as critical now as it was in 1944. The mechanisms have changed with technological advancement, but the fundamental principle endures. The March 1944 missions to Berlin, the first to be escorted all the way by single-engine fighters, marked a decisive turning point in the air war over Europe, from which Germany never recovered. From that point forward, no target in Germany was beyond the reach of American bombers with fighter escort throughout the mission profile. The systematic bombing campaign could proceed with losses that, while still significant and tragic for the crews involved, were sustainable from an operational perspective. German war production came under increasing pressure as synthetic fuel plants, ball-bearing factories, aircraft production facilities, and transportation networks all became targets that could be attacked repeatedly with fighter escort throughout the mission. The cumulative effect of this campaign, combined with Soviet advances from the east and Allied advances from the west and south, brought about Germany's defeat 14 months after the first P-51s reached Berlin. The paper drop tanks served throughout this final period of the war, produced continuously through 1945, with thousands manufactured each month. The tanks were used not only by P-51 Mustangs, but also by P-47 Thunderbolts and P-38 Lightnings, extending the range of all American fighter types operating over Europe. British fighters also used paper tanks extensively. The Royal Air Force's Mustang squadrons employed them for long-range missions over occupied Europe and Germany, conducting fighter sweeps and ground attack missions deep into enemy territory. The efficiency of paper tank production freed aluminum and steel for other uses, such as airframe, construction and engine manufacturing, while providing the range extension necessary for strategic operations. This optimization of resources, matching production methods to requirements and prioritizing efficiency over tradition or aesthetic preference, exemplified the industrial approach that characterized Allied operations throughout the war. Today, historians studying the air war over Europe recognize multiple factors that contributed to Allied victory. Numerical superiority in aircraft and pilots provided quantitative advantage. Technological advantages in areas like radar and communications enabled better coordination. Strategic bombing of German industry and infrastructure degraded production capacity. The cumulative effect of sustained combat operations depleted German resources faster than they could be replaced. Each factor contributed to the eventual outcome. The P-51 Mustang and its paper drop tanks were important elements in this multifaceted campaign, but not the sole decisive factor. The air war was won through the combined efforts of multiple fighter types, operating in coordinated campaigns, bomber forces that pressed attacks despite losses, industrial production that replaced losses faster than they occurred, pilot training programs that maintained quality while increasing throughput, intelligence gathering that identified critical targets, tactical innovation that adapted to changing conditions, and sustained commitment of resources over years of conflict. The paper drop tank represents one component of this larger effort, notable because it so clearly symbolizes the industrial advantages that underlay Allied success. The technical files maintained at Rechlin documented American capabilities with professional precision. German engineers recorded specifications, performance data, construction methods, and production estimates, with the thoroughness characteristic of German technical work at its best. These records, preserved in various archives including portions captured by Allied forces at war's end, provide historians with detailed contemporary assessments of Allied equipment as seen through German eyes. Reading these documents today, with the benefit of historical hindsight and access to American production records, reveals that German technical analysis was largely accurate in its assessments. They correctly understood American capabilities and limitations. What they could not change was the strategic reality those capabilities represented. Understanding that an enemy possesses overwhelming advantages does not provide the means to counter those advantages when they are rooted in fundamental disparities of industrial capacity and resource availability that cannot be overcome through tactical adjustments. The legacy of the paper drop tank extends beyond its wartime use to encompass broader lessons about appropriate technology and practical engineering. It serves as a reminder that effective solutions need not be sophisticated or technically impressive. The best solution is not always the most sophisticated or the most elegantly engineered. The best solution is the one that meets requirements while being manufacturable in the quantities needed, within the time available, using accessible resources. This principle, taught powerfully by paper drop tanks falling across Germany, remains relevant in military and civilian applications today. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.